Hi, and welcome to the University of New South Wales and the School of Mathematics and Statistics. My name is Thomas Britz, and I'd like to look at problem 95 and show you the solutions. This is from the course 3411, and this problem is about RSA encryption. So this is a very well-known and very well-used encryption scheme, and although it's been around for quite a while and is used quite a lot, as I say, it's a very simple scheme. Mathematically speaking, it's extremely simple, and it's quite easy to use as well. So let's encipher a message and then decrypt a message in part B. So we are looking at the message hi, and we have to somehow encrypt it. So we've got a H and an I, and we want to encrypt each of those symbols. And the way that we're going to do it is use this table over here. So the H will correspond to a 10, the number 10, and the I to the number 11. Now what we do with those two numbers is then use the numbers that we have here. So this N is the modulus that we're going to be working over, and E, that's the encryption exponent that we're going to use. And we use it very simply like this. 10 to the power of E is just 10 to the power of 55, and then here we've got 11 to the power of 55, and we work out what this number is modulus 555. Oh, sorry, 551. So mod N, or in other words 551, and you work out that that's equal to 409, and 11 to the power of 55 mod 551 is 182. So you can work out that by hand if you have a bit of time, otherwise just use a calculator and so forth. This is not too hard or laborious to do. This gives us our enciphered or our encrypted message, hi, and that will just be these two numbers here, 409 and 182, and we have enciphered our message. There it is. In the second part, in part B, we have to decipher a message. For that we need to do pretty much the same thing as we did in part A, except that we need a decipher key, a deciphering key. Here we had a number, a key to encrypt, but we need another number to decrypt. And it turns out that that decryption number is just the inverse of this number modulus phi of n here. So we need to find that decryption exponent. So first of all, we have to calculate phi of n. So that's phi of 551, which is phi of, and this is equal to 19 times 29. If you have a close look, yep. So these are two primes, so that's phi of 19 times phi of 29, which is then just 18 times 28, which is 504. So that's the modulus that we'll be dealing with in part. To find the decryption exponent. So we need to find E, the inverse of E, mod this number here, 504. Now, you might have divine inspiration and see that this is, of course, well, some number. But if you don't, then you could find this inverse by using the Euclidean algorithm forwards then backwards. So let's try to do that. So we have 505. Let's write phi up here. 505. We have that 504 and 55 are co-prime, so we can use the Euclidean algorithm on these two numbers and get that their GCD is 1, and then we can use that to find the inverse of E. So 504 is 9 times 55, that's 495 plus 9, and then we use the Euclidean algorithm again, so now we're using it on 55 and 9, so that's 6 times 9 plus 1. Oh, that was quick. So we found that the GCD of these two numbers is indeed 1, as we knew. But more importantly, let's go backwards. So 1 is equal to 55 minus 6 times 9. That's using the first equation there. And then we can substitute 9 by 504 minus this term here. So let's see, instead of 9 we have 504 minus 9 times 55. So if we collect the 55s, we've got 1 there, we've got minus 6 times minus 9 of the 55s, that gives us 55 55s. And then we have some of the terms involving 504. Now, modulus 504, this cancels out and thus leaves us with 55 squared. So in fact we see that 55 is its own inverse, mod 504. So we see that D, which was the inverse of E mod 504, is exactly just 55. So in fact we have that the decryption exponent is exactly the same as the encryption exponent, which is of course very rarely the case. That's not true in general, but in this case, well, they coincide. Okay, so let's decipher this ciphertext. So again, just like in part A, we have to take some numbers, in this case 302 and 241, and we have to raise them now to the power of D to decrypt them. So this happens to be the same number, so maybe just to make that clearer I should write D here and before we had E. Of course the calculations are the same, but they could have been different had the exercise or the problem been slightly different. Now you have to work out what these powers are, mod, and now we go back to N, or 555, sorry, 551, and then you work out what that's equal to, and that gives you 17 and 13. So they are nice numbers. In particular they're nice because we're expecting a message to do with letters of the alphabet, in which case we'd like that these numbers were less than or equal to 28. If they're not, then we've probably made a mistake somewhere. Okay, what's 17? And what's 13? Well, let's figure that out. So, what's 17 and what's 13 in this table here? Well, let's have a look. 17 is O, and 13 was K. So, this is our message. So, the message, let's say M for message, was just OK. And that does sound like a plausible message, so we are probably correct. And there you go. Okay, thank you very much.